All right, this is Engineering a Compiler, Chapter 1 Summary. So the book depicts a compiler as a source program going into the compiler, and then the compiler produces the final program. And the compiler is made up of the front end, which converts the source program into an intermediate representation, which is just neither the original code, it's just a representation of the original code, right? Then the optimizer does work on that intermediate representation and creates another intermediate representation, right? And then that's passed to the back end, which creates the final program. The front end is made up of a scanner, a parser, and then elaboration. And then the optimizer is based up of operation one, and then it just for as many operation optimizations the optimizer decides to do, right? And then the back end is made up of um, what is it made up of? Shoot. Oh, instruction selection, instruction scheduling, and then register allocation, right? So the front end has the scanner. The scanner converts the strings of characters into words. So it identifies all the words in the language. So for example, if you had C++ code and you'd have like int age equals 10, it would identify it would identify age as the variable name, and then the equals the assignment operator, right? It would identify all of those, right? Then the parser checks to make sure that those words make sense in the language, right? So if you had like in C++, like int equals 10, right? It would, although these are all real words that you can use in the C++ language, right? Just the scanner would parse out all these words or identify all these words. The parser would say, oh, you can't have an integer named int because it's a reserved word, right? So that's what the parser does. And then the elaboration is like a better parser, right? So it checks things that simple grammar can't catch, such as type checking, right? Then after it does all these things, you have your first block done, and then we move on to the optimizer. The optimizer does things to optimize the code. So some things that it might do is like check if a variable is used, because if a variable is not used, it doesn't need to compile it, right? Another thing it might do is rewrite allocations inside of a loop. So for example, if variables never are changed inside of a loop, it doesn't need to reassign it to a register every time the loop um, loops back, if that makes sense. So, and then there's many other things that the optimizer can do. Then onto the back end, the instruction selection, it chooses which instructions to use. This is also somewhat of an optimization because um, like for example, if you're multiplying by 2, you could just use the add operation or add instruction if that's faster than the multiplication instruction. I'm not sure if the backend actually does that optimization in the selection part or if the optimizer tells the backend to do that. But that's an example of another optimization. Then after all of the instructions are selected, it uses the instruction scheduling. It can run sometimes, well, some instructions can be like more than one, how do I say this, like operation, right? So some instructions might take 3 like units of time and some might take 1. And as long as the ones that take 3 units of time don't rely on any of the previous operations, you can run them like at the same time, right? So it reorders the instructions to ensure that no time is wasted, if that makes sense. Then register allocation. When the backend um, creates variables and whatnot, usually there's more variables than there are registers in the computer, right? So what the register allocation does is it will determine what variables it's going to keep in the registers and which ones it's going to push onto the stack, right? Just to be able to save the variable, right? So that's the last step before the backend finishes the final program. One note on intermediate representation is that all pieces of the compiler are separate. So if you wanted to create a new language, you could simply just write a well, you can create one that writes the language into the same intermediate representation and then use someone else's optimizer and backend, right? So if you write a new front end for like some like new C language, right? You could pat you could write a front end to create the intermediate representation of that new C language, and then use the normal C optimizer and backend to be able to work on like almost every computer. So that's very helpful, and separating them like this allows easier ways to add new machines and languages, right? Because if you have like a new like machine that you want to like write all the code on, all you really need to do is now rewrite the back end, and the front end and optimizer will still work, and the back end will now include your machine, right? So that allows like separating them into three parts like this makes it very easy to add new languages and add new machines, and that's a good thing overall.